Good. Okay. So entitled confidence intervals and sample size for proportions. Okay, so there's two issues in this section. Building a confidence interval for an unknown population proportion. And then also determining the size of sample we would choose to be a certain percent confident that our sample proportion does not stray any more than a certain number of units away from the unknown population proportion. We've seen we had sample size problems back in the last week when we were building confidence intervals using our Z interval. All right, so when we get down to section 7.4, hopefully we will be able to construct a confidence interval for a population proportion and also determine the minimum sample size for finding a confidence interval for a proportion. All right. Suppose 10% of all people are left-handed. 3% of the people have green eyes. 2 out of every 5 adults went to college. These are examples of proportions. So a proportion, ladies and gentlemen, is another name for a percentage. Okay. The proportion of 10% can be expressed, of course, as a decimal, 0.1, or as a fraction, 10 over 100, or as 1/10, reduced fraction. If X people in a population of size N have a characteristic of interest, then the population proportion of people with that characteristic is lowercase p, that represents the population proportion, is going to be equal to X, the number of people that have the characteristic of interest, whatever that might be, divided by the population size. So that's how you find the population proportion. But just like we indicated last week, oftentimes we don't have the time or resources to pull everything in a population. And as a result, it's very difficult to compute a population parameter, if not impossible. For that reason, we tend to use inferential statistics and using our sample evidence to try to infer what a population parameter value is. If X people in a sample of size lowercase n have a characteristic of interest, then the sample proportion denoted as P with this little hat symbol. So that's a little hat symbol above the P that represents the proportion of a sample. So P hat is equal to X, the number of objects or items that have a trait of interest, divided by the size of the sample. Okay. Okay. The letter Q is used to refer to what is called the complementary proportion. Q, ladies and gentlemen, is always going to be equal to 1 minus P. It basically consists of all the items in a population, n minus X, that do not share a characteristic of interest divided by the population size. Likewise, Q hat is going to be always equal to 1 minus P hat. And that would represent all items within a sample that do not have a trait or characteristic of interest divided by the sample size. Okay. All right, here's an example. A survey of 80 households found that 17 of them had a landline phone installed. Find P hat and Q hat, the proportions of the sample with and without a landline phone. So our sample size is 80, and of the 80 households, 17 have landlines. That is the characteristic of interest or the thing of interest. So the sample proportion, P hat, would be 17 divided by 80, which would be 0.2125, or we know that is 21.25%. Q hat is going to be 1 minus P hat, or in this case, the number of households that do not have a landline, which is 63 over 80, which is about 78.75%. So notice Q hat and P hat always add up to 1. Okay. Just as we saw with the sample mean last week, being a point estimate for an unknown population mean, well, ladies and gentlemen, we use the sample proportion as a point estimate for the unknown population proportion. But the problem with that, just like we discovered last week, is that we have no measure of how accurate our sample proportion is in trying to estimate the unknown population proportion. For that reason, we like to construct a confidence interval, because we do have some measure of accuracy because we set the level of confidence. So therefore, an interval estimate or a confidence interval for the population proportion is preferable to a point estimate and is based on the sampling distribution of all sample proportions. And ladies and gentlemen, it's a well-known fact that as long as the sample size is at most 5% of the population size, the sampling distribution of all sample proportions is approximately normally distributed. And the mean of that sampling distribution of all sample proportions of all samples of a certain size extracted from a parent population is going to be mu sub p hat. And that is going to be equal to the population proportion. The standard deviation of the sampling distribution will be equal to the square root of p times q divided by n. Now, oftentimes we don't know the population proportion p, and therefore we would also not know q. If that's the case, then we normally estimate the standard error of the sampling distribution of the sample proportions by taking the positive square root of p hat times q hat divided by n. Lowercase n is the size of your sample. So therefore, as long as n times p hat is at least 5 and n times q hat is at least 5, the margin of error for our interval estimate will be our z-variate, which comes from the standard normal distribution. And of course, our critical z-value depends upon our level of confidence, times the square root of p hat times q hat divided by n. That's your margin of error that will be used to build confidence intervals. Okay. So therefore, the confidence interval for an unknown population proportion p is going to be the sample proportion minus the margin of error to the upper endpoint, which is the sample proportion plus the margin of error. So your unknown population proportion will lie in between these two values. And we would be, a certain level of or 1 minus alpha times 100% confident that that is the case. All right, here's an example. We can revert back to our landline phone example that we had in the past. Of 80 households, 17 had landlines. They want us to find a 99% confidence interval for the population proportion of all households in the entire population, which could number in the hundreds of thousands or millions that have landline phones. We previously calculated the sample proportion, which is 17 divided by 80, which is 0.2125. Q hat is going to be 1 minus p hat, which is 0.7875. Now, the critical z values that correspond to a 99% level of confidence would be 2.58. And we discussed in detail how to find these critical z values or t values last week using our inverse z or inverse t function on our calculator. Or to find critical t values, some of you may have used the table in your appendix, the t table, for lack of not having inverse t on your function, your calculator rather. The sample size is 80, so n times p hat is 80 times 0.2125, which is 17. That's at least 5, and n times q hat is 80 times 0.7875, which also is at least 5. Therefore, we can take faith in this confidence interval here. And to find the lower endpoint, we take the sample proportion, which is 0.2125, minus the critical Z value, which is 2.58. Again, it corresponds to a level of confidence of 99%, times the square root of P hat times Q hat divided by your sample size there. So it looks like your margin of error is about 0.1180. So your lower end point of this 99% confidence interval is going to be about 0.0945. The upper end point would be about 0.3305 here. Okay. And so therefore, how can we interpret what this is saying? Well, ladies and gentlemen, we can interpret this confidence interval as saying we are 99% confident that between 9.45% and 33.05% of all households in our entire population have a landline phone. Okay? And we're 99% confident in saying that. So that's the beauty of the confidence interval, is that we have some ideas to the measure of accuracy between our sample result and our unknown population result. Any questions how we built that confidence interval manually there for an unknown population proportion? All right, how can we build this confidence interval using our calculator? Well, let's bring it up and we'll show you. Well, let's see if we can bring this up here. Okay. What we'll do is we'll go to our stat, and then we'll go over to tests. And then we'll go down and select the function that is the one prop z int function. There it is. So the one prop z int function is short for one proportion z interval function, which means this function will compute a confidence interval for your unknown population proportion using your z interval, or z probability distribution, which is your standard normal probability distribution with a mean of 0 and a standard deviation of 1. Okay, so just make note that this is the function used for section 7.4 to build a confidence interval for an unknown population proportion. All right, so let's dive into it. Notice for this problem here, X was what? How many of our households had a landline of 80 that were randomly surveyed? 17. The sample size was 80. Level of confidence is 0.99. And ladies and gentlemen, you have your answer. There's your 95% confidence interval. Notice your calculator also computed the sample proportion, which is 0.2125, which is 17 divided by 80. Any questions how we use this one prop z int function to build a confidence interval for an unknown population proportion? So you can see that obviously that function is a lot more efficient than doing the problem manually, but nonetheless, the manual way is worthwhile in the sense that it helps us to see the ingredients, if you will, that go into computing this confidence interval. It also enables us to determine the margin of error and its size, whereas this function does not enable us to do that explicitly. Okay. Okay. Any questions about that there? Let's now go to our textbook, and I'm gonna, have a little bit of fun here. All right, let's go to our textbook.
Of course.
All right, so this is gonna be section 7.4. It's entitled Confidence Intervals and Sample Size for Proportions.
There it is. The speaker.
All right, classwork number one is pretty simple here. I want you to do problem number one. What they want you to do is find P hat and Q hat, given this information here. Classwork number one. All right, this one is pretty simple. All you're gonna do here is define p hat. And you're gonna just take x and divide it by n. So of our sample of size 40, 30 of the data values exhibit a trait of interest, whatever that might be, divided by 40. So p hat is going to be 3/4, which as a decimal is going to be 75 hundredths. And therefore q hat always being equal to 1 minus p hat is going to be 0.25. Any questions how we got that there? That's your answer there. All right, that's classwork number 1. Okay, let's go on down here now. And I'd like you to try to do problem number 4 here. Now, I would like this problem to be done, ladies and gentlemen, both ways, manually and with the calculator. And I'll tell you what, hold the show here. Let me go back and grab the formula here for the manual construction of that thing here. Get my snipping tool out here. Okay, let's go back to the textbook now. All right, that's the manual way of constructing the confidence interval. I want you to do this manually and also using your one prop z int function on the calculator. In 2019, 1.1% of the cars sold had a manual transmission. A random sample of college students who own cars revealed the following. Out of 128 cars, 8 had manual transmissions. Estimate the proportion of college students, of all college students who drive cars with a manual transmission, that have a manual transmission with 90% confidence. So they want you to build a 90% confidence interval for the proportion of all college students who drive cars with manual transmissions. Build a confidence interval manually and also using your one prop z int function on the calculator. That'll be classwork number 2. All right, so number 4. In 2019, 1.1% of cars sold had a manual transmission. Random sample of college students who own cars revealed the following: out of 128 cars owned, 8 had manual transmissions. Estimate the proportion of college students who drive cars with manual transmissions with 90% confident. So we know we're talking about a level of confidence, which is 90%. That means alpha is 10%. Alpha divided by 2 is 5%. So that leaves 5% of the area allocated to the lower and upper tail of the standard normal distribution. Therefore, our critical Z value is going to be 1.64. You could find this by using your inverse norm function and typing the area of 0.05 with a mean of 0 and standard deviation of 1, and that would give you a critical Z value there. The sample proportion is going to be X divided by 128 of the 128 college students that were randomly surveyed who do drive cars. 8 of them drove a manual transmission. So the sample proportion of those who drive a manual transmission is 0.0625. Q hat is the complementary proportion, which is 1 minus B hat, which is 0.9375. Then, ladies and gentlemen, we can build our confidence interval manually here. This is going to be P hat minus your margin of error. This entire thing is called your margin of error, E. It's your critical Z value times the square root of P hat times Q hat divided by the sample size of 128. This is going to be your upper end point of your 90% confidence interval, which is a sample proportion plus 1.64 times the square root quantity here. When you get done dialing that up, after subtracting and adding your margin of error from the sample proportion, you get this for your 90% confidence interval. And therefore, that would be your 90% confidence interval. Now, how do we interpret what that interval is saying? Well, we could interpret this interval this way. This would be one way to interpret it. We are 90% confident that between 2.7% and 9.8% of all college students who drive a manual transmission. That's how you would interpret that confidence interval. Okay. Any questions? Did anybody get that computed manually correctly?
Yes.
Okay. That's how you manually compute a confidence interval. You can see that it is a little bit tedious, and that you do have quite a bit of calculations to go through, but that would be how you tackle it manually. Now, I would also like you to be able to merge this manual way of doing things with the calculator way of doing things. And so we're going to show ourselves how to compute this same confidence interval using our TI-84 calculator. Okay. First of all, any questions about the manual way of how we computed this here? Okay, now, so how would we do this on a calculator? Well. We go get the machine. So stat test and go down, scroll down, do you run into the one prop z int function? X is the number of items in a population that exhibit a characteristic of interest. In this case, our characteristic of interest is whether a college student who drives a manual transmission. And we know that of the 128 randomly surveyed college students who drive, 8 drove a manual transmission. The confidence level is 0.90. And now we can calculate the confidence interval. And there it is. So that reflects the same thing that we obtained manually. Between about 2.7% and 9.8% of all college students who drive do in fact drive a manual transmission. And we are 90% confident in saying that. So hopefully we know how to do this problem both manually and with the one prop z int function. Any questions? All right. Okay, now problem number 5. Let's see, ladies and gentlemen, if you can negotiate number 5, both manually and with the calculator. You do that one, we'll call that classwork number 3. Or if you're getting tired of labeling your classworks, just call it a classwork, okay? All right, number 5, try that one. Manually and with the calculator. All right, so for number 5, we are to build a 90% confidence interval for the population proportion of students, of all students, that say that cash is their top choice for a graduation gift. So a 90% level of confidence is going to have the same critical z-value, 1.64, like the last problem. It says 88% of students prefer cash for graduation. That's going to be the sample proportion, proportion, if you will. All right. Q hat is 1 minus P hat, which is 1 minus 0.88, which is 0.12. So we can build our confidence interval here. This is your margin of error. This is your margin of error. Sample proportion plus minus the margin of error is going to be 0.8323. Sample proportion plus your margin of error.
I have a question.
Yeah.
Why I thought P would be, why do we use 0.88 and not 0.85 for P? Because I thought it was 85% of students preferred cash.
Well, we go back to problem number 5 and just read this thing here. It says 88% of students said that cash is their top choice for graduation. If 125 students were surveyed, find a 90% confidence interval for the population proportion.
Oh, I read 85. My bad. I'm sorry.
88%. Okay. All right. So 88% is the accepted as the sample proportion. Minus your margin of error. Now, when you work this margin of error out here, which is your critical z-value times the square root of p hat times q hat divided by your sample size, your margin of error is about 0.0477. So when you subtract that from p hat and add it to p hat, you get your lower and upper end point of this 90% confidence interval, which is about 0.8323 and 0.9277. So we can interpret it this way. We are 90% confident that between about 83% and 93% of all college graduates prefer cash for a graduation gift. Okay, and there you go, ladies and gentlemen. That's how you interpret what that interval is saying. So 90% constant. That's manually how you put this thing together here. And then we will turn it over to the calculator and show ourselves how to do it using the one prop z int function, the one proportional z interval function. First of all, did anybody get this confidence interval here?
Yep.
Okay, so now, you know, there might be some round off error here going on, and you might have a slightly different result. Again, if you, when doing Alex, if you are convinced that you did the problem correct, but it's just a matter of a small discrepancy and round off, you can bring it to my attention. I'll go and I'll take a look at it. And, you know, if I feel that it's just a matter of a slight discrepancy in rounding, I'll probably award you all the points back. Okay. Normally, when we're comparing two populations, when we build confidence intervals or do hypothesis testing, if you're off by a slight decimal amount, the conclusion will not be changed at all anyways. For that reason, slight round off discrepancies are not a big deal when doing hypothesis testing, or in this case, when we're building a confidence interval. All right. Especially when you're comparing, like I said, two different population parameters. We'll see that in the future. Or when doing hypothesis testing. Okay, let's do this problem over again using the calculator this time. So let's bring up our machine. And let's go get our stat tests. Go down and grab the one prop z int function. Now, ladies and gentlemen, what is x? X is the number of, in this case, the number of students in our sample out of 125 surveyed that prefer cash. Well, you don't put 88% in here because 80.88 is a proportion. It's not a number. We just need a number. So how are we going to find x? Well, we're going to find x by just noting again what p hat is and how p hat is found. P hat is x over m. So if I were to solve this equation for x, I'd multiply both sides by the sample size. So therefore, this implies that x is equal to p hat times n. So therefore, to find the number of students of the 125 students who prefer cash, you just take 0.88 and multiply it by the sample size of 125. And that's going to give you x, okay? Now, you can do that right within the environment of your calculator. All you got to do here is type in 0.88 times 125. So you can see out of 125 students, 110 prefer cash. That's what x is. And n, of course, is a sample size. 0.9 is your level of confidence. Calculate, and you get the same confidence interval. There you go. All right. And notice p hat is 0.88. So that's how you find x if they don't explicitly give you x. All right. All right, so let's see here. Okay. All right, so for our next class work here, you can go ahead and try number 6 here. Then when you get done, see if this Time Magazine survey, which is 37%, see if that's actually in your confidence interval, okay? So go ahead and do number 6, and this time, ladies and gentlemen, you can do you can just build a confidence interval using your calculator. You do not have to do this no, I'll tell you what, I still want you to do it manually. So I want you to build this confidence interval, 99% interval manually and using your calculator. And then in the end, we're going to see if this 37% is actually found in our 99% confidence interval. Okay, go ahead and do that number 6. Do it both ways. All right, so for number 6, we're building a 99% confidence interval, which means alpha is 1%, and 1% divided by 2 allocates an area of 0.005 in the lower and upper tail of the standard normal distribution, which if you use your inverse norm function and cite this as the area to the left of the critical z value you want to find, you'll get a critical z value of 2.58. P hat of 205 students surveyed, 60, what was it, 68? Believe in ghosts, or believe that 65 believe that places are haunted. That would be about 32% of students that were surveyed believe that certain places are haunted. Q hat is 1 minus P hat, which is 0.683. Building our constant interval, P hat minus your margin of error. Lower endpoint, P hat plus your margin of error is your upper endpoint. 2.58 is your critical z value times the square root of P hat times Q hat divided by the sample size n. Margin of error is like 0.0838. Subtracting and adding that from 0.317 gives you your lower and upper endpoint of your 99% confidence interval here. And so therefore we are 99% confident that between about 23% and 40% of all college students believe that certain places are haunted. Now, if you go back to the latter part of this problem, it indicates that according to Time magazine, 37% of all Americans believe that places can be haunted. Notice, ladies and gentlemen, that's in pretty good agreement with our 99% confidence interval for just college students. In the sense that 37% is found in our confidence interval. It lies between 23% and about 40%. So the beliefs of college students extrapolates to all Americans in general. Interesting. Okay. Did anybody get that confidence interval there?
Yep.
Okay. Oops, hold on a second here. Let's do this on our calculator now. And so we go to stat tests, one prop z int function. 65 was it? 65 of 205 randomly surveyed college students believe that places are haunted. 99% level confident. And we get the same confidence interval there. Okay. All right. Good. And so we're discovering how to build confidence interval. The other part of this lecture, ladies and gentlemen, is conducting what's called a sample size problem now. So let's go back to our PowerPoint presentation and finish this up now. Okay. Recall, ladies and gentlemen, that the margin of error for the population proportion confidence interval is this right here. E is the margin of error, which is your critical z value, depending upon your level of confidence. 1 minus alpha times the square root of P hat times Q hat divided by n. If you take this formula, ladies and gentlemen, and solve it for the variable n, and how would that be done? Well, I can show you quickly. Just a little bit of algebra. Let me show you how to manipulate this formula and solve it for the variable n here. First of all, I'm going to divide both sides by z, in which case I will have e divided by z is equal to the square root here. Now, how do we get rid of a square root? We square it. So we're going to square both sides of this equation. Therefore, this implies that we have E over Z squared is equal to, when you square a square root, the square root disappears. So we're left with P hat times Q hat divided by N. All right, everybody see that there? All right, now, if I multiply both sides of my equation by N, I'll get the N on the left side. And when you multiply the right side by N, the N's would what cancel out. So be left with P hat Q hat. Finally, to solve for N, I divide both sides by E over Z squared. And that gives me my sample size. So this is going to be divided by E squared over what? Z squared. And another way to write this is to say P hat times Q hat times Z over E quantity squared. So you could cite it that way. Or you could cite it as P hat Q hat times Z squared over E squared. Either way there, but okay, so that's how you solve for N there. That's a little extra for your money here. Now, so ladies and gentlemen, you might want to have this handy or memorize this before you dive in and do any Alex problems. Pretty important formula. It's called a sample size formula, which will enable us to be a certain percent confident that the difference between our sample proportion and unknown population proportion will stray no more than E units from each other. Okay. Now, if we have a good approximation for the sample proportion, obviously we're going to use P hat. But ladies and gentlemen, this is important. What if we do not have a good approximation for our sample proportion in the problem? If that's the case, then what we do is we default by using 0.5 for both P hat and Q hat. This is very important because you're not always going to have, you know, a sample proportion when you do a sample size problem. Sometimes you're going to have to just by default put in 0.5 for both P hat and Q hat. And we do that because that maximizes the product of P times Q. And of course, we always are seeking to maximize our sample size. Do you agree? When in doubt, choose a large sample size to reduce sampling error. All right. The disadvantage of using 0.5 for P hat and Q hat, if we don't know what P hat is that our sample size oftentimes is inflated, where we don't necessarily have to use one as large as what we are given. We're computing. So if we do know P hat, it's always wise to use the sample proportion. But sometimes, like I said, you just don't have that luxury, in which case you just don't have any choice. But then you're going to have to just assign 0.5 to both P hat and Q hat. Okay. All righty. And this table down here is just showing that the maximum product of P hat and Q hat does occur. Okay, does occur when P hat and Q hat are both 0.5. So the idea again is if you don't know P hat, always err on the side of caution and err on the largest possible sample size you can. Because again, when it comes to sample size, larger is better. That's always the case. So it would not hurt to have an overinflated sample size, one that you did not necessarily have to choose as large but it can only be better. You never want to err on choosing a smaller sample size than is what is minimally required, because that will lead to an error in your result. So always err on the side of caution and assign 0.5 to P hat and Q hat if you do not know P hat. All right. All right, here's an example. It gets back to that landline phone example. Remember that one? We previously constructed a 99% confidence interval for the population proportion of households with phones. Our sample size was 80 and our margin of error was 11.8%. Was it 11.8%? Yeah, Yeah, 0.118, okay. How large a sample would we need if we wanted a margin of error of at most 5% for the same problem? Suppose we did not want a margin of error as large as 11.8%. We wanted only an allowable margin of error to be 5% as to the maximum difference between our sample proportion and unknown population proportion. Well, we computed p hat to be 0.2125. Since we know p hat, we will use this value of p hat as opposed to defaulting its value to 0.5. U hat is 0.7875. We want to be 99% confident in selecting our sample size. Therefore, our critical Z value is 2.58. Our allowable margin of error is 5%, which has a decimal is 0.05. All right, ladies and gentlemen, so let's substitute things into the sample size formula. And when you go through the arithmetic and crank this out, you can see that we would have to choose a sample of at least size 446 to ensure that our sample proportion to ensure that we are 99% confident that the difference between our sample proportion and population proportion is no more than 5%. Okay. Ladies and gentlemen, suppose we did not know p hat. Well, in that case, we would have to default by setting p hat, q hat equal to 0.5. We put things back into the sample size formula, crank it out, and notice if we don't know p hat, we would have to choose a larger sample size of at least size 666, which is almost 50% larger than our original sample size. So again, the moral of the story is if you know the sample proportion, by all means, please do use it. That will ensure that your sample size is of minimum value. If you don't know p hat, and you have no choice but to assign 0.5 to both p hat and q hat, which means that your sample size is probably going to be inflated. But who cares? I mean, so what, we make an error. So what if we choose larger than 446? We choose 666. That only means our result's going to be what? Even more accurate. Do you agree? Because the larger size of sample you choose, the smaller the sampling error is going to be between your sample and population result. So it doesn't hurt to choose a larger sample than 446. It doesn't hurt to choose a sample size 666. Did we have to choose one that's large? No, but it doesn't hurt anything. It only helps if you do. Okay. All right, now, unfortunately, on our calculator, we cannot do a sample size problem, directly. So we kind of have to know this formula here. That's why it's important to have that at your disposal. Okay. All right, let's go back to our textbook and finish up here today. Let's see if we can maybe do a sample size problem. All right, let's see here. All right, number 15. This will be another classwork here. Overseas travel. A researcher wishes to be 95% confident that her estimate of the true population proportion of individuals who travel overseas is within 4% of the true proportion. In other words, ladies and gentlemen, we want to be 95% confident that our sample proportion is within 4% of our true unknown population proportion. Therefore, what size sample would we have to choose? If in a prior study, a sample of 200 people showed that 40 traveled overseas last year, I want you to conduct a sample size calculation for this situation. And then I want you to do it again if we don't have any estimate of our sample proportion? How large of a sample should be chosen in that case? So there's two different problems here. The first problem assumes that we know p hat. P hat is going to be 40 divided by 200. Crank out the size sample, minimum size sample that you're going to need. Suppose we don't know p hat. This is the second question they're asking then. How large of a sample would we have to choose then? All right, so go ahead, do those two sample size calculations. We'll throw this into our classwork here. Okay, for number 15. We are going to have a level of confidence of 95%, which indicates that alpha is 5%. And alpha divided by 2, or 2.5%, of the area is allocated to the lower and upper tails of the standard normal distribution. Being the case, our critical Z value, if you use your inverse norm function on your calculator, type in 0.025, with a mean and standard deviation of 0 and 1 respectively, you'll get 1.96. Your sample proportion is of the 200 people randomly surveyed, 40 traveled overseas last year. So your sample proportion is 40 over 200, which is 0.2. Q hat is 1 minus P hat, which is 0.8. Plugging the values into your sample size formula here, going through the arithmetic, you get a sample size of at least 385 needs to be selected. So in order, ladies and gentlemen, to be 95% confident that our sample proportion will stray no more than 4% away from the unknown population proportion, we need to choose a sample size of at least 385. If we don't know anything about our sample proportion, then by default, we will assign 0.5 for both P hat and Q hat. In which case, we put the new values into our sample size formula, keeping the Z value the same and also our allowable margin of error the same, cranking it out, and we would have to select a sample of at least size 601 to be 95% confident that our population proportion will be within 4% of the actual unknown population proportion. Did anybody get these computed?
Yep.
Okay, so these are sample size problems here. Ready? All right, I just got one more for you, ladies and gentlemen. We'll call it quits. Number 19. Just do this one here. One more sample size problem. Number 19, U.S. fitness guidelines. According to the World Almanac, 35.2% of men ages 18 to 44 meet the U.S. fitness guidelines. Whatever that is, how large a sample is necessary to estimate the true proportion of all men that are fit in this age group within 2.5 percentage points with 90% confidence? Go ahead and do that. Conduct that sample size problem there, number 19. Last classwork. All right, for number 19. May indicate that according to the World Almanac, 35.2% of men ages 18 to 44 meet the US fitness guidelines. So I would probably use that as my P hat at 0.352 or 35.2%. 0.352, and then Q hat is going to be 1 minus this, which is about 0.648. Now, 90 was it 90%? It was 90% confident has a critical Z value about 1.64 or 1.645. I tried it with 1.64. An allowable margin of error is 2.5%, which is 0.025. I get about 982. When I tried 1.645, I got like 987, no, a little bit bigger than this. So you can see that round off does, impact your answer, even if it's just kind of like a slight round off, if you will. Reason being is because you're taking the ratio of 2 decimals here. And so if there's just a slight difference in round off of one of those decimals, that does have a rather large impact as to what the final quotient is going to be. So, because of round off going on here, and if you wanted to be extra safe about things, you could just default P hat and Q hat to be 0.5. That way, you know that even if your sample size is going to be a little larger than what we originally calculated up here, you can rest assured that your result's only going to be more accurate than this result here by choosing a sample size like this, because this is going to be your maximum sample size. All right. Maximum minimum sample size that we would want to choose here. And I worked this out too. And I think I got like 1097 or something. So yeah, I got 1075 here. I'd call it about 1076 here. So again, when in doubt, if you're out in the field here, this is not that much larger of a sample than this. Okay. What is it? About 90 more observations or so. So I would probably opt for this rather than this. This is only going to ensure that your sampling error is smaller between your sample proportion and your unknown population proportion. So again, when in doubt, when you're doing an investigation, always try to err towards the larger sample size. Always. Never the smaller sample size, always the larger sample size. Okay. And again, ladies and gentlemen, with these sample size problems, if Alex squawks at you when you feel like you've used the correct formula, you put things in correctly, you have the critical Z value, the correct critical Z value, albeit maybe a small minor difference in round off. Just bring it to my attention, the problem number, the assignment, your name. I'll go back, I'll take a look at it. If it looks like you did everything pretty much correct, you're close enough, I'll give you credit. If it's way off though, of course, then there obviously was an error. Okay. And you may not get all your points back on the problem. But so just keep that in mind, especially for these sample size problems, because I'm noticing for this one, there is a slight discrepancy. In fact, the answer they have in a textbook for this problem is 994. And for the life of me, I don't see how you can get that. I tried all different things. So again, I would probably opt for at least about 1076 for your sample size to be on the safe side. Okay. All right. So just keep that in mind if Alex gives you a problem with these sample size problems as far as the round off error is concerned. All right, ladies, I'll get to your chapter 7 quiz. I'll see if I can get that open. I'll email you the due dates on those if there's any changes for the quiz and the exam. So always check your email. And other than that, you have a good day. I'll stay on the line for a couple minutes if you have any questions.
I had a question.
Yep, go
Um,
ahead.
yeah, could you go back to it was classwork number one, the problem number one. Could you go back to that one?
Yeah, okay. Uh, that was way back, okay. That's this guy right here, number one. They just wanted you to find P hat and Q hat. So P hat is nothing more than X divided by the sample size, okay? So P hat is gonna be 30 divided by your sample size of 40, X over N, all right? Which is gonna be 0.75. Which as, yeah, that's what it would be as a decimal, or 3/4 as a fraction, all right? And then Q hat is gonna be always 1 minus P hat. So that's gonna afford us, what, 0.25? Or 1/4. All right. That's what it would be. That was classwork number one.
Okay. Okay, thank you.
All right, that's all there is to it, yeah.
And Professor Mark,
Yeah.
I have a question. It's not about the work we did today. I missed our Zoom on Saturday morning, I think, so I was just wondering if we could try to reschedule it.
All right, let me think. Because I'm trying to think, I got something to do, I think tomorrow morning, I gotta run my wife somewhere. But, I'll have to get back with you, okay? I gotta look at
Okay.
my schedule, and I'll try to set aside some time, okay? But
Okay, no
I will email you back, okay?
Okay, thank you.
Yep, you're welcome.